Okay, welcome everybody. I have an attendance sheet. This is so I get reimbursed for the snacks. If you're a student, you can just write down Heidelberg University or something for your institute. Okay, and with that, I'll hand over to Maria to introduce.
Yeah. Okay. All right. So, welcome, Gaël. So I'm very, very happy to introduce our speaker today, who is a very prominent figure in the field of stellar physics and solar physics in particular. And this is how I also came across many of your papers, and that all started with the sun a few years ago. I'm not sure to what extent you will go in this direction, but Gaël is really the person to think about the next directions in stellar evolution, solar evolution, and this I hope something we will learn about. So now let's see. You're rather junior, and you did your PhD in 2017 at the University of Liege with under the supervision of Professor Marc-Antoine Dupré and Dr. Daniel Riese, who are both also very well-known experts in stellar physics and asteroseismology, I believe. And the PhD thesis was on inversion techniques in asteroseismology. And then Gaël moved to Birmingham to work with Bill Chaplin and Andrea Miglio, who are also very active in stellar surveys, in space-based surveys, but also in follow-up, spectroscopic follow-up of stars. And I don't know, what was your project there in Birmingham? Asteroseismology, stellar evolution. Okay. And then you moved to Geneva in 2018 to join the group of George Mayney to work on interacting stars, right? Star-planet interactions. Then you had a grant, your own Swiss National Foundation grant, Ambizione grant, I believe, right? So until 2024, you were involved with the supervision of students and postdocs, and now Gaël is back to Liège as a FNRS fellow. So this is, I think, something that will probably, that's a very promising development, yes, and where you continue to work on theory of stars, theoretical helioseismology, theoretical asteroseismology, but also, and this will probably be the subject of the talk, the prospects for the next generation planet hunter, PLATO, which is starting shortly. So many of us are here interested in PLATO and maybe will be actively involved in PLATO, especially at HITS, I believe, both from the observational and theoretical perspective. And there are a few other missions. Ariel, you mentioned, Haydn, that Gaël is involved with and coordinating at the Belgian level. So Gaël had some important prizes. The IAU PhD Prize 2017, Prize of Amis de l'Université de Liège, and the Swings Prize of the Royal Academy of Sciences last year. No? So wonderful. So I think we are really lucky to have you today with us. And I will pass it over to Gaël now to introduce us to the state of the art in solar and stellar physics for the future.
Thanks a lot. I guess this works.
Okay.
Is it working?
Catherine? Oh, just a moment. It's not working. Use the microphone.
No, it's working. Okay.
Okay. Before I disconnect, I would like to remind that there will be a dinner after I think it's 6:30, if I'm not mistaken, at Hemingway's. Nice, cozy place. So please use the opportunity. All right,
Okay.
welcome, Gaël.
Thanks. Thanks a lot, Maria. So I'll try to not be too quick, too dense in the presentation. That's usually the mistake I make when I talk. As you can see, I'll be talking about solar models and why solar models actually matter for PLATO. So let's see if the transition with the slides work. Yes, it's good. So the first thing is really, why do we care about the sun? Why is the sun still so relevant in the context of PLATO? The thing is, the sun is really our calibrator when we think about solar-like oscillators and low-mass stars. It's a very important target because we have a lot of constraints. We have neutrino fluxes that give us direct access to the solar core. You could say we have mapped the nuclear reactions occurring in the solar core thanks to the measurements of neutrino fluxes. We've done a full tomography of the internal structure and dynamics thanks to helioseismology. And the sun is really a reference. When you start using a stellar evolution code, at least when I started, people told me, do a solar calibration, compute a solar model. That's how I started. And it's still a reference every time a new equation of state comes out, new opacity tables comes out, new reaction rates come out. What do? You compute a solar model, you see what happens. And so it's important also when we look at the chemical composition of distant stars, when we look at the metallicity scale, when we relate the composition of distant stars to that of the sun. When we compute stellar populations, the enrichment laws, the relation between the amount of helium and the amount of carbon, nitrogen, oxygen, what we will call the metals, is also linked to what is happening in solar models. And then in a more, let us say, intricate way, the successes of what we call the SSM, the standard solar models, have also paved the way for the large-scale analysis of solar-like oscillators. So all the successes we had with Kepler, with Corot, when we look at main sequence stars, is thanks to the fact that we could test the solar models and see that the standard solar models worked well. So the thing you have to think about is, when you're computing stellar models, there is always something that has been tested, calibrated, looked at with solar models. And if you change the ingredients, if you say, okay, we have to revise the solar models, this will have an impact on other stars. And the question, well, how well do we know the sun? Well, to do a bit of a brief introduction, the structure of the sun is mostly described. I mean, when I look at it, I see a nuclear fusion reactor. You have the reactions happening in the core. Mostly the PP chain is generating most of the energy. And then this energy is transported outwards. 70% of the internal structure of the sun in radius, 98% in mass, is dictated by radiation, by high energy radiation. So by the atomic properties of the plasma. Then 3% of the outer layers, or 2% of the outer layers, 30% in radius, convection is happening. So what happens is that the opacity of the stellar plasma increases when you go towards lower temperatures. At some point, radiation is not efficient enough to transport the energy outwards. Convection takes over. It's exactly what happened when you put a kettle on a stove. You increase the temperature gradient between the lower part and the higher part of your kettle, and at some point convective motions occur. The key part in the solar structure and evolution is that the sun is a low mass star. It evolves slowly, gigayears on the main sequence. That means that when you look at processes like microscopic diffusion, sedimentation, at first you look at the velocities, you may think, this will not have an impact. But it will, because it has time to act. So when you look at different processes like sedimentation or hydrodynamic instabilities, even if they appear at first glance not efficient or slow, on the main sequence, they will have time to act. And if you compute a solar model with microscopic diffusion or without microscopic diffusion, you see very strong differences in the internal structure. Now, how do we know this, and how did we map it? Well, at least this question of diffusion and the importance of chemical transport, it was thanks to helioseismology. So briefly, helioseismology is the observations of solar global oscillations. The only ones we have so far, or at least for global helioseismology, are the acoustic modes. So you can think about the surface of the sun as a drum, and convection is creating pressure perturbations, acting a bit like thousands of fingers hitting on the surface of this drum, and generating waves in a whole range of frequencies. And some of these frequencies will be eigenmodes of the sun. And this will be then global acoustic oscillations, global pressure oscillations that will propagate inside the sun and you will be able to essentially map the internal structure of the sun thanks to the observations or the characterizations of the oscillation frequencies. It's a bit like listening to a musical instrument and trying to reconstruct its properties from the sound it makes. And thanks, I mean, the luck we have in helioseismology is that we have decades of observations. If you think about SO, it started observing in 1996. It was decommissioned earlier this year or late last year. And we have also networks of telescope, like the BISON network, the Birmingham Solar Oscillation Network, that has observed the sun continuously. And so we have more than 7,000 individual frequencies. The last paper on that is Reiter et al. 2021, if I remember correctly. And the importance here is also that we can resolve the surface of the sun, so we can go to high degrees. We're not limited to low degrees by geometric cancellation. This is something that will come back when we'll talk about PLATO. For details, if you're interested, I would, for the theoretical astroseismology part, I would refer you to the UNO textbook. And for the solar structure and evolution, there is a very good review written by Christensen-Dalsgaard in 2021. So, the solar modeling problem, the solar abundance problem, or the solar problem or in general, is linked to something that happened in the early 2000s. So you might say in the 1990s, everything was better. I'm not saying this because I was born in the 1990s. But regarding solar models, the important part is the spectroscopic abundances that were used, the GN93, GS98 abundances, worked very well. When you computed models with these abundances, you correctly reproduced the transition from radiative to convective transport of energy down to 1 per 1,000. You reproduced correctly the helium mass fraction in the convective envelope. That is also measured by helioseismology, and that was not one of the parameters that you would tweak when you would do a solar calibration. If you look at the original paper, the Christensen-Dalsgaard 1996 standard solar model paper, the agreement is even lower than 6 per 1,000. It's about 4 per 1,000, I think, in terms of sound speed relative differences. We'll see sound speed inversions in a few slides. And then came Martin Asplund. He decided to revise downward the solar metallicity, and the models went to hell. Nothing works. They didn't reproduce the position of the base of the convective zone, didn't reproduce the helium, didn't reproduce the sound speed. And this brings us back to this issue with the solar models that most of the internal structure of the sun is dictated by radiative transport and by the atomic properties of the solar plasma. Now here, it's a long text. It's something that I found by chance, actually looking at the review of the solar models. It was a textbook generated written after a NISI workshop. And if you know, Douglas Guffey likes long sentences, so that's why the sentence is extremely long. But essentially, what they were saying is that a standard, in terms of what we call standard solar models, it's a standard at a given time. And the problem that we see in the standard solar models is that there are lots of dynamical processes, lots of physical revisions that may happen. Whether they will correct or not the solar model, that's a fair question to ask. But in practice, the physical ingredients we have in the solar models will continue to evolve. And that will come back to bite us for PLATO. Because if we start including these dynamical processes, we'll actually bias the mass, radius, and age determinations we want for PLATO. So I will not let you, you can read the quote if you want, but essentially they had a lot of fights in the early days, and there were two camps. One was led by John Bacal, who wanted to have the standard solar models that have worked extremely well and produced a lot of high quality results. And then there was Evry Schatzman, who's well known in the French community, who wanted to include all the dynamical processes that you could model. But of course, then the problem is the computation time and how realistic the modeling of these processes are. So the controversy remains. It's essentially low Z, high Z, low Z, high Z. From the spectroscopic point of view, I would say there are two sides that disagree on the amount of oxygen, for example, that you have in the sun. From the helioseismic point of view, there was no question. If you revise the metallicity, the models did not work. There was no question to be asked. Sound speed was wrong, helium was wrong, mass and position of the base of the convective zone were wrong, and the neutrino fluxes did not work either. So none of the models actually worked as soon as you assumed the Asplund abundances. And that was very clear. One key problem that we have to keep in mind, though, regarding abundances is also neon. Neon is a nasty element to measure because it's measured, at least in the young 2018, from coronal lines, and it's very sensitive to activity. So what's happening with the abundances, at least in helioseismology, what crystallizes the issue are what we call these, how to visualize it, are these sound speed inversions. So this is actually inversions from the solar data. You have the surface of the sun here, the core of the sun here, and these are relative differences. So these are disagreements between the sun and your model in percent over the course of the solar radius. So essentially, you can see in the envelope, you see slight mismatches. You have a huge bump at the transition between the convective and the radiative transport. So this is the position of the base of the convective zone that is known down to 1 per thousand. So that's also something you don't necessarily realize it, but the level of precision you're working with in helioseismology is also absolutely insane. And this is the reason why we worry so much about the issues with the models, is because these differences, although they appear small, it's like 5 per thousand in difference in sound speed, they are extremely significant in terms of precision. And so here you go down, you continue down to the solar core. So all of this is radiative. And so the effect of switching from the GN93 to GS98 or the latest 2022 abundances, the effect would be essentially similar. If you reduce the metallicity, you increase the disagreements. You can see it here. If you use the Asplund abundances, you can see that you have sharper disagreements at the base of the convective zone. The problem is that it's a measurement of sound speed, it's degenerate. And there is another ingredient that acts on these profiles, is these sound speed relative differences. This time, same model, same abundances, same equation of state, just changing the radiative opacity. So the intrinsic capability of the plasma to absorb radiation. And you can see you also have very significant differences, and not only at the base of the convective zone. So at the end of the day, what you can say from this is that this disagreements that we have are mostly a question of a couple of contributors to the capability of the solar plasma to absorb radiation. And if you look at theoretical calculations, these are contributions done by a PhD student of Anil Pradhan at Ohio State, in different temperature regime. So you have the center of the sun, so the solar core, the center of the radiative zone, or what we call the radiative mantle, and the base of the solar convective zone, so about at 2 million degrees Kelvin, where we have these sharp deviations in sound speed. You have 3 elements that contribute: oxygen, neon, and iron. And these are the ones that completely dominate the opacity in these layers. So neon is not necessarily very reliable in terms of its abundances. Oxygen, well, again, we have disagreements in the spectroscopic community, and iron is actually quite difficult to model in terms of opacity. So essentially what was happening when you were using, or when we use higher metallicity, we're increasing the amount of oxygen in the models, we're increasing the capability of the solar plasma to absorb high energy radiation, and so we have a sharper temperature gradient, we have a better agreement that we see here, there, wrong arrow, in sound speed. So if we look, it's essentially the transition from here to here. Now, in this model, it was actually a prototype of the 2021 Asplund abundances. It's just a neon increase. And you can see you keep all the elements the same, you just increase neon, you have a sharp drop. Why? Because neon is the third contributor of opacity, so the response is also very nonlinear. When you change the composition a bit, you have a nonlinear response of the opacity, and you can have drastic changes in the temperature gradient. So the other problem is that how reliable are these opacity tables? So we asked people who do these theoretical opacity computations to do comparisons of their code. We gave them conditions in temperature, density, and chemical composition. And we asked a couple of groups. There are actually 4 groups that do opacity tables. OPAL at the Livermore National Laboratory in the US, Los Alamos at the Los Alamos National Laboratory in the US also. OPAS and Square CG are 2 groups at CEA, and OP is a civilian consortium that has published opacity tables in 2004, if I remember correctly. The reference is Badnell 2004. And if you ask these people to compare their opacity measurements, or their opacity computations, not measurements, their opacity theoretical computations, on the same conditions, you see a very significant dispersion between the results. We have differences, for example, for square SCG, here you're up to 50% in differences in opacity. And these actually extend to higher temperatures. So this is worrying not only for the solar base of the convective zone, but if you go to higher temperatures, you go in the regime where you will affect the thermonuclear reactions that are happening in the sun. And that's a bit more worrying because then it can change the efficiency of these nuclear reactions. You can change the temperature response because you'll have a different temperature of the solar core. And these are for the three main elements, but we see these differences also for simple elements like hydrogen or helium. We see also significant differences, even at high temperatures where you would expect them to be fully ionized, and they should be easy to model from an atomic structure point of view, but they show significant differences. So the question that we have with the solar models, and one, I would say the state of the art regarding the solar models, is that we have an issue on the atomic physics side, both when we look at the oxygen abundance measurements, and both when we look at the radiative opacities in the solar core. And this degeneracy can only be broken if we have more reliable atomic physics calculations. So these comparisons need to be extended to other regimes also to see what's missing in these computations. Fortunately, they did actually experiments with the opacity measurements. There are three papers on the topic: Bailey 2015, Nagayama 2019, and Bailey 2025. And they're always seeing discrepancies. For iron, they see a discrepancy between the models and the experiment between 30 and 400%, which is highly significant. For oxygen, the models match the spectrum they measure. All the models work, but none work for the same reasons. If you look at the paper, they're all compensating their errors in some way, which means that these issues can actually manifest themselves in different temperature regimes, and again extend to a higher temperature regime, which can then come back to bite us when we're going to do stellar evolutionary modeling for solar-like oscillators, or even other stars. And for the solar models, well, for the solar oxygen, this is the current trend. And again, you see differences. They seem to be converging towards a value. But again, the uncertainties, the problem is that changing from here to here, or from here to here even, is very significant. The level of precision we need on these results is higher than what is currently provided. And the problem is, again, how can we push these measurements higher? This is not my field of expertise at all. But the problem is that at the level of precision we want, this is going to impact us. And this is something that we need to worry about. So this was the current state of affairs from the radiative side of things. I started asking the question, can we measure abundances in a different way? And this leads me to a slightly more technical part of the talk, that yes, you can do it using these helioseismic inversions, but not looking at sound speed, looking at the chemical composition of the solar envelope. So the way you do this, the way we do helioseismic inversions, is using these linear integral relations. So you start from the adiabatic oscillations of stars. In spherical symmetry, we assume you're an isolated star as the sun. Slowly rotating, no strong perturbations due to magnetic fields. Essentially, spherical symmetry applies. And you can then essentially relate your frequency differences to structural differences. It takes a little bit of algebra starting from the oscillation equations to get down to these integral relations. But essentially what this relation tells you, you have your observations here, your frequency differences between the sun and your model, and your structure differences between the sun and your model inside these integral relations. And so this is why I'm always showing these relative differences in sound speed. You can actually write the exact same relation for density and sound speed, for example. That's the classical one that has been used to carry out helioseismic inversions. But here what we're interested in is not density, it's not sound speed, it's this first adiabatic exponent. That is actually the way we can measure helium in stars, at least in cool stars. Because you cannot get it from spectroscopy, you have to find another signature. And that signature is provided by seismic probing of this first adiabatic exponent. If you have a perfect monoatomic gas, that value, that gamma 1 function takes the value of 5/3. Any deviation from that, like for example, if you have an ionization or partial ionization of helium, for example, gives you a dip. So this is gamma 1 minus 5/3. You see it's 0 almost everywhere. Then you have a dip where you have actually the second ionization of helium that is actually occurring here. And this signature, the waves will see it, the acoustic modes will see it, and you'll then be able to infer a value of helium from the amplitude of this deviation from this 5/3, this monoatomic perfect gas value. Or by probing the gamma 1 profile, to say it more accurately, you can get a direct measurement of the helium abundance. So why is it so? If you start from this integral relation where you have the gamma 1, you can actually write your gamma 1 perturbations as a function of state derivatives of pressure, density, helium, and the metals. And so you can get both the helium value and the metals. This is a complicated piece of work because you'll be depending on the equation of state. You have to be careful about data set dependencies. So when you do these inversions, there is one nasty thing you have to keep in mind. It's an integral relation. You have a certain number of constraints. Let's say you're working with the sun. You have 6,000 individual frequencies. You have 6,000 left-hand side here for your equation. But you still want to probe two continuous functions. You have an infinite number of unknowns. So mathematically, this is a nilpost problem. You need to assume a certain regularization. So you have to be careful about, for example, data set dependencies, about the regularization you assume to solve these integral relations. It's something that is, inverse problems and nilpost problems are very common in physics and also in engineering, actually. But you need specific numerical techniques to do this. They have been developed in geophysics and applied widely in helioseismology and asteroseismology. So these attempts, at least for metallicity, they've been done for a while with different results. And using, let us say, modern equations of states, I would say the precursor work has been done by Sergei Vorontsov in 2013 and 2014. He's the guy who measured helium in the sun for the first time in 1991, actually, already. So the problem that we have with the helium, as you've seen here, it's a large signature. The deviation from 5/3 is actually very significant. For the metals, you have two issues. If you want to get carbon, nitrogen, oxygen, you have two problems. There are very few of them in terms of mass fraction. You're talking about 1.5 to 2%. And they are actually completely blended. If you were to isolate individual elements, these are the deviations from 5/3, from these gamma 1 perturbations. You can see the order of amplitude. We're talking something down to the, 2.5 times to the -3. The nice thing is that they add up. So instead of having a single glitch signature, a sharp variation due to this partial ionization, what you will have is a valley in the gamma 1 profile. And so from this valley here, in this temperature regime, where you have these partial ionizations occurring, you can actually get an idea of what the metallicity in the sun is. The problem is, this is equation of state dependent. So you have to be careful about the physical prescriptions that are in the equation of state. So the safe approach we used here was to rely on the temperature domains where all the equations of states seem to agree. Whether that is correct, that's a work hypothesis. They seem to predict the same thing. Again, keep in mind this is physics dependent. If the physics is revised, this result will also be revised. So we did this with the size 3OS equation of state. Opal, there is a technical reason why this could not be done. I can go into the details in the questions. But what is interesting to see here is that, at least from the inversion point of view, you see all these symbols, all these dots, are the inversion results. They all match, whether we use a different data set, whether we use different reference models, we're always within the same regime. And you can see the level of precision we're reaching. The error bars are actually there, they're just extremely small. And so with this, we can actually match or try to get an estimate of the metallicity. And in this case, using various data sets, equation of states, models, opacities, it's independent of the opacities because it's happening in the convective zone. So that was a working hypothesis we wanted to check. It's validated. We get a low metallicity in the sun. Problem is, all the rest still needs to be corrected. All the other issues that I showed you sound speed, helium, neutrinos, all of this needs to be corrected. I will not show you the solution today because we don't have it. And probably revising the abundances is part of it. I'm not saying that this is absolutely correct. We're in that ballpark, but it's definitely true that if we go to the higher regime here in metallicity, this will already help a lot, depending on the element that is revised. And colleagues at the Sternberg Astronomical Institute in Moscow actually tried to go for individual elements. They managed within their analysis to actually get abundances of oxygen, and here it is carbon that they're showing, and again found a low value for their from their analysis. But again, this is equation of state dependent. All of this need to be further improved using revised equations of state. So in summary, regarding the chemical composition, where are we heading with this method? We're heading towards a low metallicity. Can the method still be improved? Yes, for sure. More data is around. Here I used oscillation modes, about 2,200 oscillation modes. There are data sets. These data sets from Johan Reiter still could be used. Well, now I think the latest he sent me was about 7,000 modes. We need to do further tests with the MHD equation of state, the third one that is on the market, that is being revised by Rainer Trampedach. He did some preliminary work and he seemed to be confirming our results. He confirmed actually our results, but this needs to be further investigated because he saw differences also in the lower temperature regime between his MHD equation of state and the other ones that are on the market. So this needs to be further tested. The other thing that needs to be tested are actually 3D effects. The sun is in 3D, at least in the convective envelope. There are 3D phenomena. What we're looking at is an average, but whether that average is always correct, that's something that needs to be tested, especially for helium, actually. And there are further tests that need to be done regarding the recent publication by Masao Takata and Douglas Goff on the uncertainties on the solar radius itself. The problem is that when you do helioseismology, you're reaching a level of precision that is so high that you need to be paranoid about everything. You need to be paranoid about any small breaking of spherical symmetry, and any variation of the radius by 10 to the -4 can actually impact your results. So this is the level of precision you're working with. Now, this is one thing for PLATO, because we need to know we need also to relate the chemical composition of stars to a precise and accurate solar reference. But the other thing we need to worry about regarding PLATO in terms of chemical composition are light elements. Why light elements? There are traces actually of the transport processes in stars. And this is going to be much more interesting for PLATO even. They have low fusion temperatures, and they can be measured spectroscopically, although beryllium is a nasty piece of work. They're required, of course, improvement in the evolutionary code if you want to follow them directly. But the important part is that they're directly influenced by what happens at the base of the convective zone. And so far, in standard models, they have been neglected. There are, again, it's this issue with the dynamical processes that have not been probed or not been inputted in the standard models. And if you look at what they do, the standard models, well, they don't match at all, neither lithium nor beryllium. So whatever the metallicity you input, this is the evolution of lithium as a function of time in your standard model. You have a bit of burning during the pre-main sequence phase because the envelope goes deep enough. And then it's just gravitational settling, slowly decreasing the value over time. Same with beryllium. The problem is the observation is there. The difference is the factor of 140 between the prediction by a standard model and the actual observations. So if you want to do this, you need to put mixing at the base of your convective zone. Now, how do you justify that mixing? That's a good question. We tried with combined effects of shear, meridional circulation, and the Taylor's point instability. We could reproduce lithium. We would completely mess up beryllium because we were transporting too deep. Because since beryllium and lithium have different fusion temperatures, you have a control on the efficiency of the mixing, but also how deep you actually transport your elements. Because you need to burn lithium, but you should not burn too much beryllium. And so in practice, you may say, sure, but these are light elements, these are trace elements, they don't matter so much for the transport of chemicals. The problem is, they actually do. If you put mixing at the base of the convective envelope, you change completely the solar calibration results. Because simply, you prevent other elements that are much more important to fall from the convective envelope. You have to imagine in the sun, you have your convective zone, and settling is just your elements falling from your convective envelope. If you put mixing at the base of the convective zone, it's like adding a sponge that will retain the elements close to the base of the convective zone. And so you prevent the depletion from the convective envelope. And so what happens when you put mixing in a solar calibrated model, and if you try to calibrate it, you try to match the observations. So this is essentially the helium evolution you'll see over time. A high metallicity model, for example, standard model, starts high, and you see a very nice linear trend. This is just settling occurring, and you match the observations. And you're too low if you put a low metallicity model. This is what you see here. But if you put mixing, you reverse the trend, and you actually see that you start lower, but since you keep more helium in the envelope, you actually end up with a higher helium abundance in the envelope at the current age of the sun or of a given star. And this has also been seen in F-type stars by Kuldeep Verma in 2017 and 2019, Kepler stars, where you could also see that, well, the effects of settling, just seeing these sedimentation happening in stars, was actually way too efficient for the F-type stars, and he needed some mixing at the base of the convective zone. And so the thing that you see in the solar models is that since you need to reproduce the luminosity at the solar age, you adjust the initial chemical composition, but that also needs, in the sun, we control things. Mass, radius, and age are known. They're not known from stellar evolution, they're known from independent observations. This kind of stuff, when you do stellar models, when you do asteroseismology, is going to impact your mass and your age inferences. So what I was saying about the diffusion velocity, you can actually illustrate it very nicely, very easily, with this kind of plot. So these are the diffusion velocities in the radiative zone of a solar model. This is a standard model, and you see the diffusion is mostly efficient at low temperatures. If you put mixing, this is this effect of this sponge layer that I was telling you about. You prevent actually settling from occurring. You're retaining the elements close to the base of the convective envelope. And so this means that in your calibration effect, you will compensate to have more hydrogen initially, so lower helium, so you can reproduce the solar luminosity at the solar age. So this is one thing that we need to worry about in the analysis that we will do for PLATO. Now, last question, you talked about the solar core. What's happening with the solar core? Well, in the solar cores, I told you we have neutrinos that are the direct traces of these burning. We can actually do a full spectrum for the neutrinos. So we can have the PP neutrinos, we can have the beryllium neutrinos, PP, we even have the CNO neutrinos now. So we can really map the energetics of the solar core. They're the direct traces of what's happening in the core. They give us the core temperature and the core composition. And what are the neutrinos saying? Well, the neutrinos saying that we need a high metallicity, even higher than what is predicted in the latest models, if you look at the basilicoidal results. And so these are all standard solar models, and these are the neutrino results from Borexino. There is a nice paper on this. There were a lot of works being done by John Gaël and Aldo Serenelli on these anticipation of the metallicity of the solar core and the constraints that you could get from the solar neutrino fluxes. And there was this very recent letter right after Borexino, right before actually Borexino published the CNO neutrino fluxes. It was Douglas Goff writing this paper, anticipating the solar core metallicity measurement or something like that. And in this case, you favor a high metallicity again. So how do we correct that? How do we check on that? When that I don't know, because if we start looking at non-standard models, they don't work. So these are all high metallicity models. And you see the PP flux, beryllium flux, boron flux, and CNO fluxes. I don't even think that's the latest Borexino, the latest Basilico result. I think it would actually be even higher. So if you use a standard solar model with the 1996 opacities, you're good. You can match everything, but you don't match lithium. You don't care about rotation. Your convection is purely MLT. You don't worry about overshoot. You don't worry about anything. And this works. If you use the latest opacities from Los Alamos, you get the blue crosses. You're not matching them. As soon as we revise the physics, it's not working. It's like, you're walking on a tightrope and you get pushed in one direction and you try to overcompensate and then you end up falling on the other side. It's the same with rotation. If we add any mixing to reproduce lithium or beryllium, we reduce the core metallicity, and we end up not matching the neutrino fluxes, whatever the abundance scale we use. Here, I use the MAG et al. 2022 abundances. So this is a problem that essentially states that it's more general than just a question of abundances. What is a potential solution? Well, there have been papers by Masanobu Kunitomo and Tristan-Guillot on the topic, where one potential solution could be planetary formation. I will let you look that up, because I will not explain all of that here. But this is a very interesting hypothesis, on top of other effects that could come into play, like these opacity revisions or nuclear reaction rates uncertainties, both on the beryllium reactions and the N14P actually reaction in the CNO cycle, the bottleneck reaction of the CNO cycle. Now, I've bothered you with the sun for so long. Why does it matter? Why do we care about this for PLATO? Well, for PLATO, we want 10% in age. Now, if you look at the PLATO objective, I think they say, oh, it's about 15% in mass. No, if you want to have 10% in age, you need 3% on mass precision and 1% on radius. And the problem you will have with PLATO is that it's not going to be a controlled environment like the sun. You're going to be looking at wider ranges of metallicities, wider ranges of mass. And the sun is a very controlled environment. I told you we know the mass, the radius, and the age of the sun. And in this case, the inference problem characterizing these global parameters, the internal structure of these stars, becomes more complex, more degenerate, because you're not controlling the boundaries of your problem. And the data quality also decreases dramatically, because we don't resolve the surface of stars. We have geometric cancellations for all these modes, and instead of having about 6,000 low, medium, and high degree modes, we actually have only about 40 of those, only low degree modes. So we cannot do this full tomography of the internal structure of stars like we do for the sun. We can get some constraints, some global constraints on their core, but we cannot get to the level of precision we have with helioseismology. So what does the data look like in this case? So this is a power spectrum of 16 Cygni A. And you can see the data looks like this. So you have your radial modes, dipolar modes, quadrupolar modes, octupolar modes, so L equals 0, 1, 2, 3. If you've done quantum physics, these are characterized by spherical harmonics. It's just a spherically symmetric eigenvalue problem. It's the hydrogen atom, essentially. And what these look like, you see a very regular spacing in frequency that you can actually use to define seismic constraints. But at the end of the day, what you're going to try to match is the oscillation spectrum of these stars, or you're going to try to match the separations or the ratios of separations and things like that. The problem is you're going to be in a very difficult case. Again, what's the underlying problem? It's an ill-posed inverse problem. And the best case scenario is case A. This is a figure that comes from a paper by Pierre Roudaillet. And I mean, I'm very bad at doing figures, so I borrowed this one, because this is an excellent illustration of what the inference problem looks like when you do stellar structure inference. The best case scenario is this one. You have precise constraints, an accurate mapping from the data space to the model space, and a limited space for your solutions. This is what you want. This is the optimal case. In practice, you can be in a biased case. You have well-defined constraints, precise constraints, but in your modeling framework, you can actually have something that is completely mismatched, and you end up with a precise, with inaccurate result. This is what happens for the ones who do stellar asteroseismic modeling if you don't take into account the surface effect. That's what happens. You have a very precise result, but you're inaccurate. Other case, you have a very precise set of constraints, but degenerate solution. A good example of that are red giants without seismology, for example, if you want to get the constraint. The tracks are all at the same place in the HO diagram, so you'll have a very degenerate solution. And this is the solar case. You have very precise constraints, but you don't know what's happening with the model because you have other ingredients that are limiting you. In practice, you may say, oh, we have seismology, everything. We can actually avoid these degeneracies. Even for the best Kepler stars, we see them. So this is a subsample of the Kepler legacy sample. So the best solar-like oscillators that have been studied by Kepler. And this was a work by my former student, Jérôme Bétrizet. And so he redid the modeling of all these stars using different constraints. So the individual modes, all frequency combination ratios. And then he compared them to values in the literature. This is the reference paper for the Kepler legacy sample modeling. And you can see the spread in mass. This is the same data, right? And depending on how you do the modeling, well, sometimes you don't get the same results for the mass and also for the age, of course. And sometimes your uncertainties can vary a lot depending on what you're using, whether you're using individual frequencies or these frequency combinations. And so the problem is that this is the kind of work that you need to do if you want to know the actual precision that you're delivering and the accuracy that you're also delivering on your results. Because if you have very precise results, but they're completely biased, they're not necessarily very useful. So in this case, the problem is also that some of these stars, as you can see, are more massive. They're starting to have convective cores. And then the problem gets worse because you have to take into account the feedback of the hydrogen in the convective core. And a quick word on these obsessions that we have on stellar age. We actually never measure them, right? They're always model dependent. It's not in the data. It's never going to be in the data. In the best case scenario, in the main sequence, you would be very happy if you have the central hydrogen abundance. But the relation between hydrogen abundance and age is actually not necessarily linear. So this is just I would say, a very basic illustration that I did from using some evolutionary models. You see, in the best case scenario, it's very linear. But as soon as you have a convective core, like in this case, for example, you can see OV means overshooting. For the ones who do stellar modeling, this means that at some point the convective core appears, and it can feed more hydrogen in the core. And in this case, it's absolutely not linear. So your age, if you see a stellar age, it's always model dependent. There's no way around it. And this means that if it's model dependent, it's physics dependent. It's dependent on all the ingredients that have been put in your stellar evolutionary models. So can we check for the problems with the physics? Yes. Fortunately, yes. We can try to get a grasp on what's happening based on the physics that we have at hand in the evolution code. We can try to quantify the biases. So this was a work by Jérôme in 2022 on Kepler 93. It's, I would say, a similar benchmark to the PLATO benchmark. The idea is to do what we call a two-step modeling process. So first you have to really well map your parameter space. So you would do typically an MCMC modeling. For the technicalities, we would use the AIMS software that was developed in Birmingham by Ben Rendell and Daniel Rees. So you do an MCMC, you map your parameter space. So you have your global minimum. Then how do you look at the bias of the physics? Well, you have to change the physical ingredients, one by one. You change the opacity tables, you change the reaction rates, you change the transport of chemicals, and you rederive the solution. You cannot do that with an MCMC on the grid because you would need to recompute the entire grid. What we do is we do a local analysis, so local minimization. Technically, for example, the Levenberg-Marquardt algorithm would do the trick. You start from your global solution, and you see how that minimum shifts with the variations of the physics. And so in this case, this is what we got for Kepler 93. These are the PLATO objectives, the PLATO precision requirements. And you can see we're not doing too bad even for the age. We're within the requirements for Kepler 93. And fortunately, the PLATO requirements were well designed. It's for a solar twin. It's not for one of those nasty F-type stars with a convective core. The problem with that, it's very expensive. You need to compute all these models. And for example, I showed you in the previous plot some models for 16 sig. For 16 sig, we did about 40 to 45 models. You will not be able to do that for all the stars in PLATO. You'll have thousands of them. This will not be doable. So the question is, how do we keep improving and how do we improve these physical ingredients? Because it's also, these physics analyzers are also limited by what you have. Like the Los Alamos opacities are not perfect. They will be revised. The nuclear reaction rates, they will be revised. The prescriptions we have for the chemical transport, they will be revised. So these analyzers are also given at a specific point in time in the history of stellar structure and evolution, if you want. How do we constrain the physics from seismology? You have to step out of the evolutionary framework. And these inversions that we've been doing for the sun, you have to extend them to other stars than the sun. And in this case, you have to be careful about what happens with your inversions. I will not do a lecture on, or a seminar on asteroseismic inversions here. It's an entire field of itself. But the idea is that from the combination of evolutionary modeling and static analysis, you can have this loop. So what will be coming out of the PLATO pipeline will be this global minimization on a fixed grid. Because PLATO will have a grid of stellar models with a given physics and will provide you parameters. From these parameters, mass, radius, age, and a structure, if you want to test the physics, one way to do it at a limited numerical cost is to do local minimizations on the fly, and you vary the physics. And then you can estimate the systematics. But again, you're limited by what you've input in your stellar evolution code. If, for example, your stellar evolution code doesn't have a certain network of nuclear reactions or a certain equation of state, you'll not be able to test it. And if you want to implement it yourself, it's often a nasty piece of work to do all of that on your own. If you want to step out of your evolutionary framework, you have to do the static analysis. And then you can hint at revisions of the physics. Some targets that are very important in this respect are not necessarily the solar, like oscillators. Red giants, subgiants, or gamma Doradus stars are prime targets to actually do this because you have different types of oscillations that give us access directly to the core condition. So to conclude on this, and I hope I was not too long or too quick, on the solar problem, from these techniques we have developed, we seem to be looking for a low Z. But again, this is physics limited. We should not forget about some other elements. And we have to be careful about these equation of states effect. For the radiative part of the structure, we really have to push people who compute opacities to give us more, to do more comparisons and to give us access to more data so we can actually look at what's happening inside their code. In terms of transport and macroscopic effects, we need more light elements measurements for other stars than the sun, because this will affect the transport you have over time and will come back to bite you for your mass, radius, and age inferences. And in practice, we have to be very careful about the physical inputs we have in our evolutionary models. You have your parameter card, and then you have what's under the parameter card. And the danger in stellar evolutionary computations is not what's in the parameter card, it's what you don't necessarily see. It's everything that is under the hood, including the numerical procedures that are used in the stellar evolutionary computation. So with this, I would like to thank you for your attention and to do a small piece of advertisement. We're doing 2 conferences in August in Liege, one on stars and planets, an IIU Symposium 408, and then the PLATO Stellar Science Conference will actually happen in Liege also right after the IIU Symposium. This one is free of any registration fee, if you're interested. And with this, I thank you for your attention.
Thank you very much. So I will open the floor to questions, particularly students and postdocs. If anyone is question. And I allow the awkward silence. No. Usually the awkward silence works. All right. Here we go.
Hi, thank you. So when you were talking about the high Z, low Z with respect to oxygen in the sun, it seemed like the discrepancy between the high Z and the low Z was like a factor of a few.
Yeah.
Yeah. Would trying to get oxygen abundances in any like primordial solar system objects help you with that, or are those not pure enough to inform what's in the sun?
I don't think they would be pure enough to actually inform us in that respect. I think the most reliable estimates we have so far come from the direct estimates in the atmosphere, in the photosphere of the sun. So you have the atomic lines and the molecular lines that can help us. Those are the ones that at least from a spectroscopic point of view.
Thanks.
More questions? Back.
But that's
for the interior models, they are not impacting the measurements we have for the interior models. For the atmosphere models, for the photospheric measurements, I think there have been tests, and they seem to have a bit of a limited impact, I would say. I think Maria would have a much better opinion on that, the impact of magnetic fields for the inferences of abundances at the photosphere. I think that this remains relatively limited. For helioseismology, it's not that important. That doesn't mean that magnetic fields don't play an important role in the solar structure. If you think about what happens at the tachocline, for more evolved objects, they play a key role. There you have to consider them. But here in the case of these, the interior models of the sun, they're not considered, and they don't impact the results that much. There was a paper by Antia in 2003 where he looked at these effects, and they seem to be relatively small. The other thing that, although if we talk about local helioseismology and the efforts of the group of Laurent Gison, for example, they have been looking in their simulations at these effects in local helioseismology. But for global helioseismology, the impact is too small.
Thanks, Gaël. Since you were talking about Bayesian approaches and systematics, so maybe not for all of them, but for some, typically the surface effects, these could be mitigated using marginalization techniques. Have you looked at that?
I only heard half your question. So can you speak a bit louder?
It's the sound, the problem, or you didn't hear, or? Oh, okay, sorry.
I couldn't hear your question. So that's the
sorry. So you talked about Bayesian techniques and also systematics, even though not together. Or well, maybe some of the systematics, not all of them, but some of them, typically surface effects.
Yes,
they could potentially be mitigated using marginalization techniques. Have you looked at that?
No, at the moment, to mitigate the surface effects, what we're using are the frequency combination ratios to erase them. So that's one way. But to be honest, I don't worry so much about the surface effects when it comes to PLATO. If you can, they will impact the results. It depends on how you do the modeling. The problem for the systematics, and the one that will be more difficult to track, are the ones inside the evolution code. Those are the ones that are more difficult to track. For the surface effects, I think they can be mitigated, and I think also that the progress that is being made in patch models and 3D simulations will also help to that respect, although you will not deal with the energetics of the oscillations because you will still be computing adiabatic oscillations. But that can be mitigated to some extent, I guess, and that's something that you can, at least you know it's there, and you can relatively quantify it, as you said, by marginalization and by using other seismic indicators. It's one way to deal with it.
Any more questions?
Thank you for the talk. You mentioned a lot about the, of course, the evolution of the sun, but sun is rather unique in terms of the it being a single star. So what do we need to do when we want to look at the binary stars or more systems with more compact star systems with more compact numbers? So what do we need to include when we are thinking about these systems? I'm asking this because, of course, these studies will be included, the evolution of the sun, the knowledge of this will be included in those, the evolution of those models. But what do we need to do when we want to include the effects of the environment to your approaches?
So if you're doing really joint modeling of a system, if the binaries are close enough, then you have to worry about the deformation and the potential excitation by tides. So there have been observations of tidally excited pulsators, and in this case, you actually need to compute properly the deformation of the structure to actually to actually then the oscillation computations themselves have to take that into account, and the geometry of the modes will be changed. Then you really need to compute the joint evolution, taking into account the impact of one or the other. The danger when you do binary modeling, at least as it's done in some code, and again, down to my understanding, is that sometimes these effects are neglected. It's evolved like two single stars, and this can be a bit dangerous, at least from the pulsation point of view. If they're close enough and the geometry of the modes is deformed, then you have to be careful, because then you will not be predicting the same frequencies. It's the same with fast rotation. If you have a fast rotating star, it will become oblate and the geometry of the mode will change. And you'll need to take that into account if you want to reproduce the observations.
don't see any more hands. So I'll just remind you all, there'll be dinner with the speaker. And if you're interested, come on down and you can find the organizers, and I'm sure there's space to join. So with that, let's thank our speaker again.
Thank you.